This video is about the demo of Lab 10 to reproduce a circuit for binary phase shift keying using discrete components. The objectives of this labs are understand the operation of BPSK modulator and demodulator to generate BPSK signal both on hardware and software tools, to implement synchronous demodulation for recovery of message. To properly understand this experiment or lab, students must go through this experiment and read it entirely to become familiar with its objective and how we will perform by using hardware and software. Before performing the hardware, we will go through the schematic diagram for performing this experiment. The shown figure is to is the schematic diagram for generating BPSK. So by using this diagram, we will generate BPSK. As it is shown in the diagram, we will use 5 TIMS modules, audio oscillator for generating 2 different signals, TTL and sine wave, phase shifter that will use to phase shift the sine wave, and further multiply it with the line coded signal to generate BPSK. So by generating, we have to generate a line coded signal. For this purpose, we will use a sequence generator and line code encoder. Sequence generator needs some TTL to driven. That TTL will be the bit clock, which is the output of line code encoder, and the output of sequence generator TTLX will be given to a line code encoder, and the clock of line code encoder will be the TTL generated from audio oscillator. So the output line code encoding scheme which you want to use will take it from line code encoder and give its input to a multiplier. So the one input of multiplier will be the line coded signal, and the second will be the phase shifted sine wave, which is generating from an audio oscillator. And the output of multiplier can be shown on oscilloscope by choosing channel 1 or channel 2. Now we will discuss about the demodulation of BPSK signal. The shown schematic circuit diagram is used for demodulation of BPSK. So as we see previously that we are using line code encoder to encode our signal into a particular line coding scheme. So to decode this, we have to use a line code decoder and a decision maker what kind and what would decide the level of the signal, and LPF will be used to recover our signal of particular frequency and eliminate the highest frequencies. Multiplier will be used to multiply the 2 signals, and one will be the BPSK signal and other will be the phase shifted signal of sine wave. So we have to tune that phase shifter and we will see a recovered signal from line code decoder respectively. So we have to implement these two circuits as for generating BPSK and for demodulating BPSK. So we will now implement these two circuits on Teams module. So as we discussed earlier, for generation of BPSK, we will use audio oscillator, phase shifter, a sequence generator, line code encoder, and a multiplier. So now we will implement the decoding circuit for BPS. For this we will use a phase shifter, multiplier, a tunable LFP, a decision maker, and a line code decoder. So we will take a stolen carrier from audio oscillator and its output to a multiplier, and one of the input of multiplier will be the BPSK signal, and the output of multiplier will go into the LPS. The output of LPF will be given to a decision maker, and bit clock of decision maker will be taken from a line code encoder, and the bit clock generated by decision maker will be given to a line code decoder, and output of decision maker given to the port of line code decoder. The output, you can see its output on channel 2 D1. So after completing the circuit for generation of BPSK and its demodulation, we can see our output on oscilloscope. The, the yellow wave represent the BPSK and blue wave represent the message signal. And now we can see your we can see. Now I change and look for the reconstructed message that we receive it or not correctly. So the received message signal and the transmitted message signal has been shown on a oscilloscope. Yellow one is the received message signal and blue is the transmitted message signal. So now we just connected the circuit to perform a discrete generation of APSK using discrete components, and discrete components has been connected. We are taking our output from this port, and two op amps, we use two op amps and two signal generator has been using. We are using one give us the 1K sine wave, the other is the TTL digital signal with a frequency of almost 100 hertz, and the 10 kilohertz uh, sorry 1 kilohertz input has been given to this point, and 10 kilohertz input has been given at this point, which is in the form of digital signal, and this input was the sine wave. So we are taking our output across this IC, and output has been displayed on a oscilloscope. Further, we give 5 volts op amp input to op amps and other ICs by using a battery power supply from this terminal. So the circuit has been implemented. Now we will check the what is output is on oscilloscope. So from circuit, let's check what will be the output on oscilloscope. So this is the output we are getting on our oscilloscope, and it is the generated wave for BPSK. That's it for a discrete components of this experiment. To implement the discrete components experiment to produce a BPSK using discrete component, students should note the results to fulfill their manuals. That's it for this experiment.